Thank you, everyone who's joined us. We're just going to wait 1 minute to let people kind of come in to the webinar right as the hour gets started. So please just sit tight. For those of you just joining us, we're just going to wait a few more seconds to let people trickle in, and then we'll get the webinar started for today. All right, we've got people still coming in, but we've got a lot to cover today, so I will get started. Good afternoon or good morning, depending on where you are. My name is Harrison Treves. I'm in the communications office at the National Renewable Energy Lab and on the DuraMAT team, and I'll be providing technical support for today's webinar. Thanks for joining us. Before we get to the actual presentation, I've got just 2 quick housekeeping slides to run through so you know how this works. Everyone is going to be muted. There's 2 options for audio. Most people prefer to listen through their computer. That works pretty well most of the time. But if you have a slow internet connection or you're just having weird issues, telephone is also another audio option. It's a good workaround. Click that up arrow next to the audio button, or just leave and join again and switch to phone audio when you're coming in. If you're having technical issues, that sound isn't getting resolved or something else weird is going on, use the chat panel to message me. I'll be keeping an eye on that all webinar and troubleshooting any issues people have. If you have a question for our presenter or his team, use the Q&A panel to submit your questions. So the chat panel, that's the single speech bubble for technical issues. But if you have a question you'd like us to pose in the Q&A period at the end of the webinar, please use the Q&A panel to do so, not the chat panel. All right, with that, I'm going to hand it over to Michael Owen Bellini, also from the DuraMAT team, who's going to introduce today's speaker and give just a quick little bit of background on the webinar. Michael?
All right, thanks, Harrison. Hello, everyone. My name is Michael Owen Bellini, and I'm part of the DuraMAT leadership team. Thank you all for attending the September DuraMAT webinar. We hold these webinars monthly on a variety of topics. Our goal is to provide information about DuraMAT work and other topics that inform and influence DuraMAT work. If you're interested in finding out more about DuraMAT and our research portfolio, you can visit our website at duramat.org. So first of all, I'd like to make sure that everyone is aware of the upcoming DuraMAT Fall workshop, which will be held September 26th to 27th in Albuquerque, New Mexico. Registration is closing September 13th, so I think you have a couple more days to register for the event if you are interested. You can find more information about the event on the duramat.org website under the News and Events tab. Okay, so today our presenter is David Young. David is the manager for the Silicon Group at NREL, and he will be presenting on laser welded edge seals for polymer-free glass modules with Tim Silverman and Nick Bosco as collaborators. I think this is a pretty exciting topic with some potentially broad implications for PV module design and durability. So take it away, David.
Okay, thank you. So I check my audio is working.
Audio is working and your screen looks good, David.
Can you see my cursor?
Yes, we can.
Okay, very good. All right, well, thank you for coming to my talk. We're going to be talking about a different kind of module, or at least a test to test a new kind of module. And I'd like to thank my coworkers, Nick Bosco and Tim Silverman, for helping me with this. This was a Spark DuraMAT project. So it was a 1-year project, about $65K to pull off the work that I'm going to show you. So let's see. There we go. Yeah, so the traditional module, as we all know, is a glass module, can be at least, and it's laminated with EVA or POE, and usually some sort of other polymer maybe on the edges to keep moisture out. And this whole project actually started during a just a sit down and kind of brainstorm about what could we do to redesign the module to improve it in lots of different areas. And one of the areas that I was interested in is what could we do with adding value to the glass in order to help with the redesign. And so what came out of it was a different kind of module that basically has a rolled or embossed element in the glass, and make a little pocket for the cells to sit into, which also allows both the top glass and the bottom glass to touch each other. And then that gives an opportunity for that to be welded. And you'll see here in a few minutes that the type of weld that we're going to do is important, and it sets it apart from the previous work that has been presented on this in this area. And the other piece that we wanted to think about was, how do we get rid of polymers? Polymers are traditionally a bad player in how modules die. So really wanted to try to remove the polymers, not just the laminate, but all of the polymers, including the edge seal. So go to the next slide. Okay, so this is a familiar, this little button's in my way, this little screen is. This is a familiar graph, and you can see that there are lots of benefits if we can redesign the module the way I showed it. The first one is there's no polymer degradation, so we would remove any sort of discoloration, the delamination due to laminates, no polymer related corrosion or PID, potentially get a hermetically sealed module so we could keep out the moisture and or control the atmosphere that our semiconductor is sitting in. That would be certainly one less barrier for the perovskites if we could have a moisture-free packaging. This new design would also be easily recycled. You could get the glass, the metal, and semiconductor easily out just by breaking the glass. It's potentially less expensive than lamination. Still working on that part. There are no polymers, so you don't have to buy the polymers. And it's only local heating at the weld, so you don't have to heat up the entire module during the lamination process. There's a lot less energy involved. Very fast sealing times, which I'll show, and also low power compared to a laminator. CapEx is a little bit higher than the laminator, so that is an issue, but it potentially gives you some added value. Again, getting rid of all the degradation issues that I talked about. And it potentially could lead you to a 50-year module, so you could have a lower LCOE. So there may be some value that you're adding, and it would help pay for the extra costs if this does indeed cost more. Certainly there are challenges. You need strict dimensional tolerance for rolled glass. The metal glass feed through is known. It's used in other parts and other components, but it's not tested for PV. And then in this work, we're going to look at the mechanical strength of the glass weld. So we're going to ask ourselves, can we make a weld strong enough to actually survive in a PV module? So let's move on to that part. Okay, so the previous work, other people have tried to remove polymers and come up with new edge seals. So the back sheet is already removed in a glass model. There are no encapsulants in these modules by these other companies. Appen Solar had a module called the NICE module, and they certainly removed all the encapsulants, but they did have a polymer edge seal. Certainly Abound and Next Gen PV are also working in that area. So the next piece is a no polymer edge seal. People have tried glass edge seal. So if you look in the literature, there are a few patents and also a few papers where people have tried low melting frit to seal up the edges of a traditional module. And those suffered from not being strong enough. So any sort of twist to the module would actually break that glass seal. And there's a reason for that. And I'm going to get to that now. So the glass laser weld that I'm going to be talking about today is actually enabled by ultra-fast pulses, so relatively new lasers. I'm going to call the old lasers are like nanosecond lasers and longer in terms of pulses, so continuous wave all the way up to a nanosecond pulse laser. Those kinds of lasers rely on linear absorption of the photons into the material. So you need an opaque material in order to absorb those photons and that energy to melt the surface. And the weld is always at a free surface. And it requires some sort of frit in order to get a good weld. And but that does require that the CTE be matched between the glass that you're trying to weld and the frit that you're putting into it. So there's some issues there. But the new fast lasers, or the short pulse lasers, picosecond and femtosecond lasers, they actually are relying on a nonlinear absorption in transparent materials. So the laser we're using is actually transparent to to the glass. If you were to not focus the laser and just have it shine on the glass, it would just shine right through it and the glass would not absorb the light. But when you focus the laser, you get this nonlinear absorption, which is essentially absorption due to free electrons from the multi-photon thermal ionization and avalanche ionization. So you're stripping electrons, and then those electrons create the plasma, and the plasma then absorbs more photons. So it's kind of an avalanche sort of exponential absorption of the photon energy. So that allows you to actually focus the laser anywhere you want and deposit the energy where you want it. So in this case, you actually focus just below the interface of the glass interface, and that deposits the energy there, and it forms kind of this oval shape weld, and it doesn't require any frit. It's just using the glass that's part of the glass that you're trying to weld together. So there's no, you don't have to introduce any material. But most importantly, it's in a closed surface. So all you're doing is just melting that material and causing it to fuse together, but you're not losing any material. And there's no need for CTE mismatch because it's all the same material. So these are really important distinctions between the two, kind of the old way of welding and the new way of welding. And I'll talk about that in more detail now. The reason this is important is if you look at the stress on the weld as a function of temperature. So in the old way, as you start to heat up the weld spot, you're going to get compressive stress in that weld region. And then when you melt the surface, that stress will go away. And then you can continue to heat up the temperature of the melt. And during that time, you're actually going to have evaporation of material. So you're losing a little bit of material as you go above the melting point. Now, as you turn the laser off, you start to cool back down quickly. But now when you cool, you start to get tensile stress in that molten pool. And eventually, you're going to cross a point where you perhaps could actually cause so much stress that you rupture the glass. And in any case, even if you don't rupture the glass, you still end up in a state of high stress. And so this kind of weld, because of the evaporation of the material in this open surface, is always going to leave you with a high stress weld. Now, if you compare that to the new way, now when you start to heat up the material, you again get compressive stress. And when you hit the melting point, because it's a closed interface, you're not losing material. So you do get even higher compressive stress, but you haven't lost any material during evaporation. So now when you cool down, you actually follow back the same line and you end up at a stress-free point. So the final state has no stress in it. So that's the key point. Now you have a very strong weld that's not susceptible to cracks. And that's the key distinction between the old and the new way. All right, so here are some examples of what those welds look like. This is a really beautiful image I pulled from literature. And you can see where, again, the focal point was actually down here at this little tip. And then it kind of made a plume, like a little plasma region, which melted. And then there's also a heat affected zone, which is much bigger. But all of this is essentially fused glass material, and that's the size of your weld. And here are some examples that we took off to the right, the top view looking down, and then you can see a close-up of that circle. And then this is a cross-sectional view. This was not our work, this was from the literature, but you can see if you stack several of these together, you can overlap them and create a very strong weld, really as big as you like. So the weld is a function of the laser power, the pulse length, and the repetition rate. And it's already used in medical devices and on laser heads in manufacturing, where they fuse a glass cap onto a metal sheath that goes around the fiber optic. So it's a well-known process. And that was one of the reasons why we teamed up with a laser company that already knew how to weld. We didn't have to reinvent the wheel. They just applied their process to our samples. All right, so this is what we did. We didn't actually make a full module or even a mini module. All we did was look at the weld. Again, this was a $65,000 project, so we had to keep the scope pretty limited. So we got glass, the same kind of glass that you would find in a module, and we had it cut to strict dimensions, had it cleaned, and the edges rounded over so it was exactly what we wanted. Then we took it to Trump Laser. They did the laser welding for us under a variety of conditions. And then we brought, well, I guess this is the actual experiment. So we made a clamp so we could hold the two pieces together very closely. The gap does have to be pretty narrow, 8 microns, which could be an issue. So you might have to work in a clean room, but many of the processes in silicon are already in a clean room. So, but you definitely need the glass clamped together very well. You also need special optics to change the beam from a Gaussian to a Bessel beam shape, which kind of elongates the beam. And then this table will kind of move the sample back and forth. So here are the laser specs. It's only a 20-watt fiber laser, again, 1030 nanometers. So femtosecond to picosecond range. Pulse energy is pretty small per pulse, but again, very short. So you're dropping a ton of photons in a very short amount of time. The actual weld specs are quite a bit lower than the max specs on the laser. So only, about 3 watts are used, 400 femtoseconds, fairly high rep rate. And our translation, these experiments were about 1 centimeter a second. You can go up to, according to Trump, you can go up to 5 centimeters a second or more with this lasing process. Okay, so this is an optical image of our sample after we brought it back to NREL. So you can see these nice smooth lines, no cracks, and they propagate nicely together, and they're quite uniform. So you can, when you look under the microscope, you can see just how uniform these welds are. It's not, you'd think that there might be lots of little dots where the you might be able to see the rep rate of the laser, but you can't. It looks very uniform all the way across the line. Okay, so we brought the samples back, and again, these are small centimeter square type samples. And Nick glued them to these metal posts, and those went into a load frame. And this machine essentially rips them apart until they break, and we measure the maximum force. And so after doing that, we flipped them over and looked at them under some different tools, so you can see where the welds, either the welds themselves broke or the glass broke. So the weld was, essentially tougher than the glass. So you can kind of move up and down these images and see either where the weld was tougher or the glass was tougher. So the main piece here is getting the maximum force to rip these welds apart. From there, then we use that maximum force, which is a sigma in this calculator, in this equation, and we use the dimensions of our samples to calculate the stress intensity factor K1. And we plotted the critical stress intensity factor, so the point of taking the weld to a point of cracking or breaking, and plotted that as a function of laser power, and also as a function of number of lines, and also separation between lines. So these were the variables that we wanted Trump to explore for us. And essentially, in this limited data set, we found that laser power is a significant knob. And we found that with the right number of lines and separation, that we got some very tough welds, and the welds were essentially as tough as the glass. There's quite a range for the toughness of soda lime glass, float glass, and we found that these parameters or settings gave us a very strong weld, a very tough weld. Okay, so now we have our experimental data. Now it's time to put these into a model, a COMSOL model, and see how they would respond in a real world full module setting. So Nick had a model of a module, 2 meter by 1 meter module that he reconfigured to do a static load test. And so he calculated the displacement heat map of the module by putting this 5,400 Pascal load on it. So we're able to get the displacement, and then he modeled the weld using this figure here. So he put in the dimensions of the sample that we actually ripped apart, and modeled what that weld should look like. Okay, so then he also messed around with trying to brace the module a little bit. We noticed that we definitely needed to have a framed module, which is common, and a braced module. So we had braces at the quarter points, and we really needed that in order to decrease the amount of deflection or displacement in the module. The other thing that he discovers that we really needed embossed ribs to stiffen the glass. So that's a real departure from what we would find in today's modules. So we actually had a small little dimple in the glass in order to basically supply a support between the different cells. And at those supports, we went ahead and simulated a weld, because we know how tough that weld could be. So we simulated the weld not only on the edges, but also on these ribs that were embossed. And so again, we welded all of those areas where the glass was touching. All right, so then the takeaway is this graph. So if you place increasingly larger pressures on the module, you get more and more displacement, but the critical piece is that the driving force or the stress along those welds, here in this case it's along the edges, you can see that we never exceed the glass value or the best average weld value for the samples that we actually tested. So these are experimental data on the green line, and then the glass value is somewhere along here in the darker brown line. So along the long length, we would have passed the static load test, and certainly along the short length, it was easily passed. You can see that there are quite a bit of stress, but not anywhere near where the critical point of where you would crack the glass would be. So anyway, essentially we passed the static load test. And that was our key takeaway for this work. We wanted to experimentally measure the weld durability or the weld toughness, and then model that in a module and see if it could pass a static load test. So first cut, looks like a module that's built like this could actually pass. So it's a good first test. I'll share this as well. This is relatively new for those of you who've actually seen this presentation before, but the folks from Trump Laser reached out a few weeks ago and said that they've been getting interest for doing welds on large area samples. It wasn't for modules, it was for some other purpose. They wouldn't share with me what that was, but they've begun to design a large table that would actually accept 2 pieces of glass the size of a module. And so they've begun to design what that table would look like, what the optics would look like, what kind of laser they would use. And essentially this would be exactly what we would be using. They've described it as kind of a large sewing machine, but instead of a needle and thread, it's a laser. So the 2 pieces of glass are put between these rollers. These rollers are pressing down to make sure the glasses are touching in less than, say 10 microns. So it has to be really flat glass. And then the lasers are in parallel with each other, and they're doing simultaneous lines as they move around the laser or in between the cells. So they predict, well, they were designing around a couple of their lasers that they already have in stock, and they were showing up to 5 centimeters a second of material growth, or material kind of linear speed of the weld. So I've used that to kind of do a back of the envelope techno-economic model, which we're going to be publishing in a paper that's going to be submitted here in a couple of weeks. So that was kind of interesting that other people are thinking about this for large area devices as well. So I'll end with that and give you the conclusions that the femtosecond laser enables crack-free, stress-free glass-glass welds. Welds are nearly as strong as the glass and or tough as the glass is what I should be saying. The static load test would have been passed, so it enables the polymer-free, hermetically sealed, recyclable modules. And the next steps are follow-on funding. So I'm happy to report we're going to be involved in 2 proposals going out the door within the next month, where this idea will be a part of that. and we'll need to develop feed-throughs. Metal glass welds are definitely in the literature. It's a thing. But again, they haven't been used for PV devices, but should be a pretty easy next step. And then I'd like to weld mini modules and actually do real IEC module testing on the welds. So with that, I'll end, and thank you for your time.
Awesome. Thank you, David. I'll just remind people real quickly that we're going to ask questions now. Use the Q&A tab that should be on the bottom of your Zoom window to type your questions in. We like to take them that way so we can see everyone's questions and get through as many as possible. So we've got a few coming in. Michael, are there any there you'd like to pose to David?
I'm going to go ahead and start with the questions that are in the Q&A tab here. And then as I'm asking these, hopefully more will come in too. So we'll start off with this first question here from Billy Stanbury, who is asking whether the plasma region melting results in segregation that can leave residual stress.
That's a good question. That sounds like a glass question, so a class expert. It probably does lead to some sort of segregation, although we measured the total strength, I guess, of the weld, and so if there was segregation, it didn't seem to diminish the strength of that weld below what we already measured. So I should mention that Corning Glass is also working in this area, and they have laser welding with their glass, so they would be probably the right experts to talk about what's actually happening in the glass.
Okay. I have a second question here from Denise Roberts, who's asking about the stress test. She's asking if you pull on both pieces of the bonded metal or just one piece, and do you learn the same thing if you pull on one side versus both?
Nick, do you want to answer that?
Yeah, sure. I'm not sure I understand the question. I mean, typically in a load frame, you fix one side and the other side's attached to an actuator that pulls on it, but there's equal force on both sides. Otherwise, you couldn't pull on it. So you always pull on both sides. If you only pulled on one side, then you couldn't produce any stress.
Okay, thanks. And then another question from Anonymous here, which I think you may have answered in the talk, but I'm not sure. Was this study using tempered glass, or is there an issue with using tempered glass?
Yeah, that's always a good question too. Thanks for that. We did not use tempered glass. We actually bought tempered glass to try it, but it had a little bit of a dimpling on it, and we couldn't. The dimpling was enough that it diffused the laser, so we weren't able to get a weld. But that's certainly one of the next steps as well, to see if tempering is going to be a problem. There is one of the workarounds might be that you actually use the laser to detemper in that local region and then perform the weld. So basically release the stress in a thermal way right before you complete the weld. But it's definitely an open question.
Okay. And another anonymous question here. What's the required overlap between the welds in order to get a hermetic seal?
Well, you saw that the width of the weld, at least one of the cross-sectional images that I showed, was like 25 microns wide. So you'd probably want to overlap that, maybe a third or half in order to get the seal. I'm not exactly sure. I didn't test for hermeticity, but it's well known in the literature that these glass welds give a hermetic seal. I haven't studied that, but you can find it in the literature. Again, that's what it's used a lot in medical devices to get a true hermetic seal.
Question from Paul Stradins here. Is the rib configuration optimal? For example, would pillars work as well? And does the welding need to be done there as well?
Yeah, Nick, do you want to comment on that?
Yeah, sure. I mean, we didn't do a comprehensive study of what's required to reduce the deflection of the module to what's required. But I would say pillars probably wouldn't work full ribs might be conservative. We did both try ribs that are welded and that weren't welded, and we needed them to be welded to achieve reduced deflection of the module.
Okay, great. Question for myself here. So, this clearly has some potential implications for thin film modules and perovskites, which require a hermetic seal, replacing the edge seal with laser weld could be a big benefit there. But tandems are also an emerging topic of interest, perovskite, silicon tandems in particular. In 4-terminal configurations where the perovskite isn't on the silicon, how do you imagine handling things like the optical matching between the perovskite and the silicon?
The optical matching?
Mm-hmm.
That seems like that's a device to device optical matching problem. So you have to put an ARC coating on the bottom of one and the proper ARC on the top of the other to match there. A lot of people have a question about, if you don't have any polymers, what happens to your optics in the module? So my answer to that is put an ARC on the top and the outer surface and the inner surface of the glass, and that's solved. The NICE module out of Appen Solar, they actually showed they had improved optics without having the polymers in there. So you have to get the ARCs right, but if you can get them right, you actually can have an improvement in your optical transmittance into the cell.
Okay, thank you.
We've got a question in chat from Jason Grenier about what do weld-in facets look like using the bezel beam optics versus the ones in literature with Gaussian optics. I don't know if you looked into that, David, but
what do the welds look like?
The weld-in facets look like based on the beam optics?
I'm not sure I can answer that specific question, but I can tell you we worked with 2 laser companies. I won't mention the other one. The other one did not use a bezel optics, and they were not able to get very good welds. They could only do welds in a very controlled environment using very controlled glass pieces. And when they tried to use ours, they did not work very well. So Trump had a lot of success using our kind of off-the-shelf glass, using their bezel optics, but the other ones that didn't use it, it was tough for them. That's all I can say about that.
Yeah, thank you.
David, is there a fundamental reason why NICE modules aren't widely used right now?
I don't know why, if there's a fundamental reason. My personal opinion is that they tried to do too many things all at once. They used pressure, air pressure to keep the module together. And they also used that same pressure to press the metal onto the cells. To me, that's an awful lot to ask about pressure. But
Sure.
we had NICE modules here. Our folks have tested them. They work fine. I saw one in the Netherlands earlier this year. It was still performing. I think they just ran into money problems. When I talked to them last time, they had upgraded their line. They seemed like they were going in the right direction, and then it looked like the money just dropped out. So I don't think there's anything fundamentally wrong, but I would have done a little differently if I were them.
Okay. We have a few more questions in the Q&A tab here still. So from Elsa Kamlam, is the glass welding envisioned to be done as part of the module's assembly lines? And if so, how important is the need for a clean room environment? Because usually assembly lines are not clean room environments.
Yeah, this would be in place of a laminator. So you'd be in that environment, and you probably want to have a clean room environment, at least a small clean room, at least around the tool, because you'd want to bring your glass right out of the cleaning and blow it off, make sure it doesn't have any particles on it, and then right into the laser welder. You really can't afford to have particles on the glass. And that may be a downfall of this project, of having to have clean glass over a 1 meter by 2 meter areas could be tough. But
Mhm.
I would say you're going to have clean room. You know, silicon PV is almost all in the clean room except for the metallization step. So it's evolved to that point. You definitely need a clean environment to get a good cell. That's not the case for the modules, but maybe you need that if you're going to go this route.
All right. Another question from Paul. Would you anticipate additional heating under one sun without a polymer in the encapsulant? And how excessive do you think that would be?
Yeah, that's a good question. I don't know. I mean, you're going to be relying on, well, you're not going to have a vacuum necessarily. You can have a controlled gas in there. So you could use the gas to move the heat away from the device up to the glass. Maybe it's not as efficient as a polymer. So you could have increased heating. You could also have decreased heating too. You'd have to test that. That's something that probably the COMSOL model could simulate and test that.
Okay. And then the last question I have on the list here from Max Kuntop. So in the medical device case, to ensure a hermetic seal, are there any special patterns that are used so that if there is a failure somewhere, that hermetic seal is guaranteed?
Patterns or patents? Patterns?
Patterns, yeah.
Okay. I'm not aware of that. Yeah, one of the reports I read looked like it was just a circle. Nothing. It wasn't like a convoluted sort of pattern. Like a serpentine sort of pattern. It didn't seem to be that way. They do tend to use multiple lines, like what we did. So if one line breaks, the other line's going to catch it. But there are really nice studies out there where they use helium. They put helium in the seal and it stays. So I think these are pretty hermetically sealed.
And so you could imagine potentially using similar patterns as they use there for PV modules in order to keep moisture out for 25 plus years.
Yeah, I think we can learn from all of that literature.
All right, I think that comes to the end of the questions here. Oh, nope, one more just came in from Darshan. I'll just read this out here. So yeah, probably a common question for you. How the cells held in place, and how do you see this process helping with module recycling?
Okay.
Have you looked at the ease of the glass separation?
Yeah. Okay, so I'll take the first question. So holding the cells in place, what I envisioned was essentially what the NICE module is doing, and also what is happening up at CSU and with that, I forget the name of that company up there. But essentially, you rely on the ribbons that are soldered between the cells to essentially hold everything in place. The whole thing is just one big web and held together by the ribbons, and then they're tacked down wherever they exit the module. So that is not a big deal. There's going to be some pressure from the glass to kind of hold things together too, but there are proof of concept examples out there where you don't actually have to have polymers holding things in place. The other piece about recycling, I think the best way to do it is you just take a hammer and you break the glass, and then you have this web of metal and semiconductor separated from the glass completely. And now you can remove the metal and do other chemical processes. If you want the silicon semiconductor, you can just pull it apart. The big thing is you don't have to remove everything from the polymer, the sticky polymer. That traditionally has been a really big mess and a problem for downstream recycling, because you end up with impurities, say in the glass, and impurities in the metal. So it's just one less thing to worry about.
In the case where you are relying on the ribbons to hold down the cells, and perhaps this is a question for Nick, who's also on the call, do you think that could have additional implications for the stress applied to the solder joints, and could you have additional issues with solder joints in that situation?
Yeah, that's a great question. Traditionally in the encapsulant definitely constrains the cells, and sometimes that's good or bad in terms of thermomechanical fatigue of the solder joints. But the other thing I wanted to mention was this type of embodiment would essentially eliminate the driving force for cracking cells, since the cells are unconstrained within this glass structure. There's nothing to transmit cells from a deflected module. There's nothing to transmit stress from a deflected module to the cells. So it would be almost impossible to crack cells in this module.
Awesome, thanks. Well, I think that might be the actual last question now. So I think we can close it out there. I want to thank everybody for attending. And Harrison, do you have any final words here?
Just to reiterate from the beginning, DuraMAT workshop is coming up at the end of the month. I will put a link in the chat. It's the first kind of line in that list of events. If you're interested, check out the agenda and you can find a link to register there. Otherwise, we'll have a recording of this webinar, either slides or recording this webinar posted in a few weeks on the DuraMAT website. And we hope to see you all at the next DuraMAT webinar. Thanks so much for attending.
Thank you.